The doom and don't look up was never about politicians ignoring a comet. It was a systems architecture failure where the cost of fixing the problem outpaced the resources available to fix it. Today, that same math applies to artificial intelligence. We are entering an era where inference costs, the price of actually running AI, are rising faster than our hardware scaling can handle them. The movie's apocalypse is not science fiction. It is a hard engineering constraint involving power density and latency. This video explains why the current GPU stack cannot support mass adoption without collapsing margins, and what specific trade-offs like model quantization versus specialized silicon are solving this math problem. When we talk about artificial intelligence progress, most headlines focus on training massive models. They celebrate how fast a new system can learn from terabytes of data. But for engineers building real products, the real bottleneck is not learning, it is inference. Inference is what happens when you ask the model to do work, answering a question, predicting flood risks, or generating code in your editor. Current engineering focuses heavily on training because that feels like progress. It hides the fact that running these models at scale is where the system breaks down. Consider the DE-Luge project, which runs continental-scale flood prediction systems across the United States at 1-kilometer resolution. This requires constant, high-frequency inference to update predictions as weather data flows in. The computational load here becomes unsustainable with standard GPU stacks designed primarily for training batches. As AI shifts from experimental tools to essential daily operations, we are finding that our hardware cannot deliver consistent latency without prohibitive energy costs. We have a mismatch where the system learns fast but runs slowly and expensively. This leads directly to an economic collapse of margins across the industry. Companies are racing toward autonomous general-purpose systems driven by hundreds of billions in investment, yet the economics are failing. A tragedy of the commons has emerged. Generating AI content is cheap and fast for individuals, but reviewing it consumes significant human time. This creates a workload asymmetry where one maintainer faces dozens of pull requests daily from AI noise alone. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Take the curl project as a concrete example. The open-source community was forced to shut down its bug bounty program not because there were no bugs, but because they were overwhelmed by plausible but false vulnerability reports generated entirely by bots. The volume of work became unmanageable for human engineers who had to verify every single claim. This is the era of AI slop, high-speed generation that degrades quality and forces teams to rely on constant verification just as much as before, but at higher operational costs due to the need to catch hallucinated outputs. This dynamic has created a shift we call the reverse centaur. In science fiction, a centaur is a human augmented by a machine, combining strengths for superior performance. We are seeing the opposite: high-wage workers becoming monitored peripherals who absorb blame when AI fails. End-to-end automation often degrades quality, forcing companies to rely on human oversight just as much as before. The difference is that now these humans are paid to watch machines make mistakes rather than doing their own work efficiently. This drives up costs without delivering the promised productivity gains of full automation. The situation is compounded by a psychological trap where users treat AI as an infallible authority. Behavioral studies involving over 1,300 participants show this trend clearly. When people treated AI predictions as absolute truth, they increased the odds of foregoing guaranteed rewards by more than 3 times compared to those who trusted their own judgment. In financial terms, trusting these flawed systems led to earnings reductions ranging from 10.7% up to 42.9% in controlled scenarios. This creates a feedback loop of trust failure. Users rely on probabilistic systems that hallucinate at scale while the underlying hardware struggles to deliver consistent accuracy without prohibitive energy costs. Nearly half of Americans now use AI tools specifically for information seeking, yet 99% have used products with hidden AI features they did not even recognize were there. We are building a society where we trust machines we do not understand and cannot verify at scale. So what is the engineering solution? It requires moving beyond binary choices about adoption to specific architectural trade-offs. The first path is model quantization, which sacrifices some precision for massive gains in speed and energy efficiency. By reducing the numerical representation of weights from floating point numbers to smaller integers, we can run complex models on cheaper hardware with significantly lower power consumption. This allows inference costs to drop below the value threshold where they become a financial liability. The second path is hardware specialization through ASICs or TPUs designed specifically for inference workloads rather than general-purpose training. These chips optimize memory bandwidth and latency for specific mathematical operations common in AI models, delivering higher throughput per watt compared to standard GPUs. The choice between these approaches depends on your use case. Quantization offers flexibility for existing stacks, while specialized silicon provides hard limits on costs that make mass adoption viable. Engineers are no longer just coders, they are system architects managing this new reality of AI slop and verification costs. You must design for the review phase as much as the generation phase. The future belongs to those who can build systems that acknowledge AI's probabilistic nature rather than treating it as a deterministic oracle. If you ignore these physical limits, your product will not fail because the technology is bad. It will fail because the math of inference costs outpaces your ability to scale profitably. The breaking point in artificial intelligence is not when models become too smart or sentient. It is simply when the cost of running an inference exceeds the value it provides, forcing a collapse in margins or quality. We are standing at that edge right now. The difference between success and failure for engineering teams will be how well they navigate these trade-offs today. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.